Hello folks, so this is 2022 May-June paper 4-2 and the question number is 6. It is concerned with the chapter magnetic field. So the question states, state the two conditions that must be satisfied for a copper wire placed in a magnetic field to experience a magnetic force. So the two conditions. So the condition is that the first is that there should be current. There should be current in the wire, and the next one is that the angle between the conductor, so the magnetic field, so let us say the field lines here, and the conductor. So the conductor should not be in this situation. That means the conductor should not be parallel to the field lines. The length of the conductor should not be parallel to the field lines. So that means that they must have certain angle there. So certain angle should be there. So angle should be formed. Formed between the direction of B, which is the magnetic field, and the current here. So these are two conditions. Now, second question: a long air-cored solenoid. Air-cored solenoid means that it is simply air between the turns of the coil. Solenoid is connected to a power supply so that the solenoid creates a magnetic field. So we have the solenoid like this, and the cross section of that solenoid shows a cross section through the middle of solenoid. So we have got this is the solenoid. It is cut like this, cut in the middle, and these are the turns of the coils. This is the space here. Now the direction of the magnetic field at point W is indicated by an arrow. So the field line here, direction of field line here. Three other points are labeled X, Y, and Z. So we have got X, Y, and Z. On figure 6.1, draw arrows to indicate the direction of the magnetic field at each of the points X, Y, Z. So we have to draw the direction of field lines at each of these points. The first thing is, if the magnetic field at W is like this, the magnetic field at X should also be like this, because inside the solenoid, the magnetic fields are all parallel to each other and in the same direction. Now, directly outside that thing, it should be opposite. So it should be going like this and like this, like this and like this, and like this and like this. So it should be opposite, like this. And now here, what happens is, it should come somewhere like this. So like this, and could be like this. So this could be one of the directions of this. So it goes like this and comes like this. So it goes like this and comes like this. So these should be the directions. Now, compare the magnitude of the flux density of the magnetic field at X and W. So X and W. At X and W, they're almost equal, because throughout this whole region, the magnetic field is uniform. Apart from the edges, uniform. So that's why the values here should be equal. So they are nearly equal. Let us say they are nearly equal. And at Y and Z, it should be so at Y it should be Y and Z here. So this Y is nearer the magnet, and as it comes like this, this is farther along this field line. It is farther. So that's why at Z it should be weaker, and at Y it should be stronger. So that's why at Y stronger. At Z it should be weaker. Field lines is because as the field lines comes like this point is much nearer, this point is farther. So that's why. Now, the next page. Two long parallel current carrying wires are placed near to each other in a vacuum. Explain why these wires exert a magnetic force on each other. You may draw a label diagram if you wish. So what we can do is, let us draw the conductors here. This is one conductor in which current is flowing like this. This is another conductor in which current is flowing like this. So now what happens is, this conductor will exert a field line somewhat like this. So if I show by fingers, it should be like this. It should go like this. So this is the current here, the field lines in the second conductor should be like this. So this is conductor 1, conductor 2. So the field lines here should be somewhat like this, like this, like this. Now what happens is, so this thing is now situated in the field of influence of this. So here what happens is, we have got magnetic field here, we have got current like this, and current like going like this, left hand rule, and we see the force like this. So that's why this conductor will experience force like this in this direction. Similarly, the magnetic field due to this in this region should be somewhat like this, So the field lines will be coming here, coming towards the observer or out of the sheet of the paper like this. And what happens is, so this is the magnetic field up, current flowing there, and the force will be like this. So force will be in this direction. So the force here. So that's why there will be a force. So it's all because the first reason is that first conductor produces a magnetic field. The second conductor is in that magnetic field, then because of the interaction, then that creates the Lorentz force. Lorentz force is created. Now what I can do is, if I reverse the current in one of them, they will start to exert repulsive force. If I reverse both of them, again attractive force, and so on. So it's all because of these three facts.